Hello everybody, this is your video on chi-squared goodness of fit. I'm hoping that you already watched the intro video so you have a general idea of what's going on here and why we use chi-squared. So let's just jump into it, okay? So like I told you in the intro video, there are three types of chi-squared tests. This is the first one. It's called goodness of fit. You use chi-squared goodness of fit tests when you want to see if the distribution that is given to you of one categorical variable is valid. So they'll give you a percentage for each category and say, we expect 20% of people, places, things, whatever to fall in this category, 15% to fall in this category, 19% to fall in this category, etc. Right? And you're trying to figure out if that is valid. Okay. So like I told you in the last video, if you wanted to do that with z-tests, you would have to compare category 1 with category 2, run a test and see if those two were different, then do the same thing for category 2, category 3, category 1, category 3. Like, it would take a long time, right? So that's what we use chi-squared goodness of fit tests for. It does it all for you in one place. Super awesome. Okay, so I already went over in general what expected values and observed values are. Observed values will be given to you in the problem. Expected values you will have to calculate by doing the sample size n times the given proportion, which is p. And you're going to see what that looks like in a minute. This is a test, right? This is a statistical test. So we are still using this, the Phantoms acronym, with a couple of differences. Okay, so first difference is the way that you write the null hypothesis. There are lots of proportions, so it's easier to just say the null hypothesis is that the given distribution is correct. The given distribution of the proportion of insert context here is correct. And then your alternate hypothesis would be that the stated distribution of insert context here, sorry, it's like really windy outside to the point where, oh my God, there's a lot going on out behind me. Okay, sorry, lost track there for a second. So your null hypothesis is that the stated distribution of proportions is correct. And then the alternate hypothesis is that the stated distribution is incorrect, right? Or one of the proportions is not correct. Okay. You actually don't have to go through and state the parameter here because you state the exact parameter in the actual hypothesis. So you can skip the P step for these, okay? There's still three conditions: randomness, 10%, large counts, okay? But the large counts condition is that the expected values all have to be greater than 5. That's the rule, okay? So when you do chi-squared problems, most of the time you will have to calculate the expected values and show that they are all greater than 5. Typically what we do is we just, on that step, we say all expected values are greater than 5. And then you go on to calculate the expected values later. If for some reason they are not greater than 5, like in the second problem I'm going to do for you in this video, they are not greater than 5. There's a couple that are not greater than 5. You basically just say proceed with caution because you'll have others, like most of your categories will have expected values greater than 5. Okay. All right. So I'm going to write that for you here because I know some of you like to follow along like with me, like in actual note documents when I do these videos. So all expected counts here must be greater than 5. All must be greater than 5. Okay. Another difference is that the test statistic is chi-squared this time. So it's not T, it's not Z, it's chi-squared. And I showed you the formula for that in the last video. So chi-squared comes from observed and expected values and not mean and standard deviation. So Z and T, remember you have to calculate the mean and the standard deviation, and then you plug all those in, figure out what your T or your Z value is. Not the case here, okay? Your degrees of freedom here is the number of categories minus 1. Right, so number of categories minus 1. So like in the M&M example, there's 6 colors of M&Ms, so degrees of freedom would be 6 minus 1, which is 5. If you were doing it like, I don't know, for, I don't know, Skittles or something, right? There's typically 5 colors of Skittles, so 5 minus 1 is 4, all right? Okay, and then last difference is that your p-value comes from either the chi-squared table or chi-squared CDF on your calculator. And I will show you where this is, the chi-squared CDF on the actual calculator. Like I'll show you where it is, but I'm going to show you a trick because the calculator will just run the entire test for you. It'll give you like the chi-squared value, the p-value, all of that. So I'm going to show you where that is later in this video. Okay, keep in mind that this will give you an exact value, right? And like the test that I'm going to show you on the calculator, when you actually run the whole test on the calculator, this will give you an exact value. The table is going to give you a range. So it's much less accurate, okay? So for us, we're going to use this, the chi-squared CDF and the actual test on the calculator, okay? And you hopefully saw this in the last video, but I am going to write it out for you one more time as to what the actual chi-squared formula is, like what the calculator is doing when it runs this test and what it actually calculates. Okay, so remember chi-squared is equal to the sum, right? So that's what that fancy E is, of the observed values minus the expected values squared divided by the expected values. Like I said, your calculator will do all of this work for you. The best thing to do when you're actually running the test is to show like one example of how you would calculate this for one of the categories and then just let the calculator do the rest. Okay? So give me a sec because I'm going to scroll down so that I can get to the actual problem. This stuff makes a lot more sense when you can see it worked out, which is fairly common for these inference problems. Right? So give me a sec to scroll down and erase my screen, and I'll see you in a second. All right, so here we are at our first chi-squared practice problem. So this one is about... Hi, sorry I paused for a second.
Yes.
No, say hi, Jack.
Hello.
This is my brother.
Hello.
That's why I paused, because he came in the room, and then I just decided that he was like, we were already messing the video up anyway. So Jack, tell them about goodness of fit.
Do the number of colors match the whatever the dealership says, and the answer is usually no. That's all you have to know, boys.
He says the answer is usually no. And what happens? No. What, you don't have to do all the work because why? Yeah, he says your calculator does it for you. So sorry if you hear music in the background or random expletives. That's my brother. Yeah, that one. Okay, so this is your chi-squared goodness of fit test example. Okay, so it's just like he said, this is basically where you have a car dealership and they have a distribution of percentages that they think people will buy. So they think like about 25% of people. Oh no, public safety alert. Hold on. Okay, sorry about that. We got one of those large, like really loud, impossible Amber Alert type things, but about public safety, as if we didn't already know to stay home. There it is. Okay, so back to this problem. I've literally started this like what is it, like 6 times now? So hopefully we'll eventually get to the end and you actually will be able to see how we solve these problems. So this is a car dealership and you have this distribution of percentages that they think people will buy these cars in. And then they did a survey of 1,000 people and asked them what color they would prefer for a car. And so what we're going to try to do is figure out, basically, does this at the bottom here, the number that came up in the sample, does it match what they thought, right? Okay, so here for your hypotheses, you have HO, which here is that you just say the stated distribution of insert context here is correct. So we would say the stated distribution of car paint colors is correct. Or you could say accurate. You could go through and list each one, but like that's an epic pain in the ass. So you might as well just write the simple hypothesis. You know what I'm saying? My brother's looking at me like I'm crazy because I just said the word ass in a video to my students. What? You're right. I'm a really bad influence. He says I'm a bad influence. Am I a bad influence? You should send me a message and let me know if I'm a bad influence. I don't know. I think that's why they think I'm entertaining. No? He says, yeah, I guess so. All right. Seriously, send me a message. Let me know if I'm a bad influence because that would be like the first time in my life ever. So, okay. So there's your null hypothesis. Then your alternate hypothesis here is that the stated distribution of car paint colors is incorrect. Easy as that. Okay, then for your 3 conditions, your assumptions, it did say random sample. It's right up here. Survey of a sample of this here, right? I guess, well, no, it didn't say random sample, but like it's a sample. You can assume randomness. I wrote this problem, not the AP people, which means I forgot the word random. So don't worry about it. It's fine. Okay. Then next is your 10% condition. The sample size was 1,000. So you do 1,000 times 10, which equals 10,000. That's definitely less than the total number of possible customers here because they said this was a major car dealer. Okay. And then for large counts, just say all expected values are greater than 5. Even if you haven't calculated them yet, just say that they're greater than 5. And then you can go back later and change it if there's one that's not greater than 5. Okay. All right. Next, we got to name the test. This is a chi-squared goodness of fit test, and we're going to set the alpha value at 0.05 because that's what we set all the alpha values at. So name the test, chi-squared, and then you can literally just say GOF. You don't have to say goodness of fit. Okay, and then we're going to set our alpha value at 0.05. Okay, once you get now here to the test statistic part, you have to calculate your expected values. So your expected values are always NP. So N is 1,000 here, and P is all of these percentages that you have in the original distribution. So I calculated them for you here on the left side of the screen, but you should show the expected values somewhere. Okay, and you're going to need to calculate them so that your calculator will do all of the other fancy stuff for you. So I have 250 here for and I'm writing it at the top. I'm hoping you can see me writing it at the top. Okay, then for silver, that's 150. For blue, 5%, so that's 50. Gold is 10%, so that's 100. And then red was 20%, so that's 200. So those are your expected values. Okay. And then I need to make sure I say what my degrees of freedom are. So my degrees of freedom here, there's 6 categories. So 6 minus 1, which is 5. Okay. At this point, stop writing and go straight to your calculator. Okay. So I'm going to switch over to my calculator here. All right. So here we go. I got to move my camera. All right. So what I have here already in a list is my observed values and my expected values. So I would give you or sorry, I'm going to give you a second. I would go ahead and pause the video. If you haven't entered this data into your calculator yet, please go ahead and do so. Make sure that you label them as observed and expected, but don't just put EXP. Your calculator will think that's exponent, like the letter E, like the exponential. So I put EXP and then car behind it. Because this is a problem about cars, and then OBS observed car. Okay, so take a second, enter those values into your calculator. Okay, I'm hoping you paused the video and got to enter those values. Okay, once you enter them, go back to your calculator and see. I already I ran a different test up here. Just to make sure I remembered how to do it on the calculator. Okay, so here's how you run a chi-squared goodness of fit test. Press the menu button, then go over to statistics, all the way down to stat tests. See how you have all of these tests here, z-test, t-test, right? So a lot of the stuff that I've been making you do by hand, you can use the calculator to do. Check out the calculator video that I'm going to post later that shows you how to do all of that stuff. Remember, all this is going to do is the math part, right? So it's not going to check the assumptions for you. It's not going to write the hypotheses for you. It's not going to write your conclusion and context, right? It's just going to give you like the test statistic and the p-value, okay? So I'm going down here to chi-squared GOF. So I'm going to click that. And it asks me for my observed list and my expected list. So this is my column of observed values, and this is my column of expected values. So here, my observed list is the one with the car, so observe car. My expected list, again, is EXP, but the one with the car. And then my degrees of freedom here is 5, and I'm going to press OK. Look at that. When you run that, there's your chi-squared value, your p-value, degrees of freedom, and then there's this thing that says comp list. I'm going to show you what that is in a moment. Okay, so I'm going to switch back now. Sorry, y'all, I got something in my throat. So I'm going to switch back here. Scroll just a little bit. Okay, for the actual chi-squared statistic, you do not have to show every calculation. Just show one of them, like one of the categories, and then say ... and then equals, and then write out exactly what the calculator gave you. Okay, so for my chi-squared value, I'm going to say that's, so I'm just going to use the very first column here, the white cars. So my observed value was 260. So 260 minus my expected value was 250. I'm going to put that in parentheses, square it, divided by 250. That's my expected value. And then I'm going to say plus and then say ... just so that you show people that you know what you're doing. And then you say equals, and then the number my calculator gave me for the chi-squared was 17.0116. Okay, that's it. That's your test statistic. Okay. Next comes the p-value part. And if you remember, see here, it gives you the p-value when you run the test. So that is your p-value. So you don't have to do anything else in your calculator. You don't need a table. This will give everything to you, which is really awesome. Okay, so your p-value here is, remember, you have to write the probability notation though. So we're finding what's the probability that chi-squared is greater than 17.0116. Right? So how likely is it that we get a chi-squared value like this, or we're going to say greater than that? Because remember, this is all skewed to the right. So, and you're not going to have any values like on the other tail. So it's always going to be chi-squared greater than, and then whatever number the calculator gives you for chi-squared. And then you just write what they gave you for the calculator, which was 0.00447 0.8, which obviously is less than any reasonable alpha value we would set, but ours was 0.05. Okay, and then you go through and make your decision. Obviously, because the p-value is less than alpha, we're going to reject the null. I'm not going to write the whole thing out for you on the right side because I have it written for you here on the left side. So we would say because the p-value is less than alpha, we're going to reject the null. And we'd say there is sufficient evidence, and then I really should have said for HA, which states that the distribution of car paint colors is incorrect. Okay? So that is your conclusion and context, and that's the whole problem. Now, the last thing that you really should do for chi-squared, because sometimes they'll ask you, and it's important to know. So we know, okay, great, the distribution is different, but which ones were the most different, or which ones really didn't match up with what we thought was going to happen, which you can kind of tell if you look at the differences between the observed and the expected values. You can kind of tell which ones contributed the most. But when you run the actual chi-squared test, you'll see exactly which ones contribute the most, and that's called they call it a follow-up analysis. So if you go back to your calculator and see this thing that says comp list right here, and I gotta move my camera again. So see this thing that says comp list, and it just says, it has these brackets with the dots in the middle. It's because there's too much data for it to show up in this small space, but you can access all of that data using the VAR button, the variable button. So if you click the variable button, VAR, see how you have this thing that says stat.complist. It will show you what all of these values are. Okay, so I'm going to choose that and click enter. So these are the individual components of the chi-squared value, and they go in order. So the first one here was the white cars, right? Then the black cars, et cetera, right? So it looks like the ones that contributed the most were the 4.9, which was the second one in the list, which was the black cars, and then 3.92, that was the second biggest number that contributed to the chi-squared value. So if you add all of these values up, that will give you this value up here, the 17.0117. Okay, so in the follow-up analysis, and I'm going to go back over here, in the follow-up analysis, you would say the colors that contributed the most to the chi-squared value were the black cars and the blue cars. Right? Which makes sense because they look like they're the most different proportionally from what was expected, right? So the black ones, there were a lot of them, but the difference was pretty large, okay? And then same thing, like a 14 car difference when you have a very small number in that category is going to contribute a lot to the chi-squared statistic. So in the follow-up analysis, you would want to say you have reason to believe that the proportion of those colors specifically are different than reported, right? So the white ones may not be that different, right? The gold ones may not be that different, but the black ones for sure, and the blue ones contribute the most and are most reasonably different from the distribution that was given. Okay, so that's a whole chi-squared test.
All right, y'all. So here is another example for you of a chi-squared goodness of fit test. Okay, so I'm going to work this through all the way for you from start to finish. All right, so just remember for these types of tests, right, you don't really need the parameter step because you're going to state it in the hypotheses. Okay, so this test that we're looking at here is a principal choosing students for a survey, and we're trying to figure out if there is evidence that the principal is not choosing students according to these demographics. Okay, so remember, H stands for hypotheses. So your null hypothesis is that the stated distribution of students chosen is correct. Okay, for your alternative hypothesis, you would say the stated distribution of students chosen by this principle is incorrect. Okay, all right, remember A stands for assumptions. Okay, so your randomness condition, we're good there because they said randomly chose 60 students. So you would say SRS stated in problem. Okay, for the 10% condition, my sample size is 60, so I would do 10 times 60, which is 600, and that's obviously less than the total number of students, because they told us the total number of students was 1,600. Okay, all right, then remember your success fail condition / your large counts condition is about your expected values. Okay, now here's the thing. We're going to have some expected values that are small. Normally what you would say is all expected values are greater than 5. In this case, we're going to have some expected values that are not greater than 5. So if that's the case, if that happens in one of these problems, you would just say most expected values are greater than 5, and then you would say proceed with caution. Okay, but normally at this step, you would just say most expected values are greater than 5, even if you haven't calculated them yet. Okay, remember N stands for name the test. So this is a chi-squared goodness of fit test. So remember chi-squared is this symbol here, and then you can just label it GOF for goodness of fit. Okay, now I went ahead and already plugged in my observed values, so that's these, into a list in my calculator, and then I went ahead and calculated these expected values already. So remember, expected values are NP. So for example, this expected value is 60 times 0.672, right? And I got 40.32 when I did that, right? This one is 60 times 9.4%. This one 60 times 16.8%, etc. Okay, so these are all of the expected values here. Remember, your calculator can do this for you. You don't have to do this by hand. Okay, so I have 1.08 here and 2.88. So see how you have a couple of these expected values that are less than 5. Normally in like a full-on AP question, this probably would not happen. But if it does, just go back to your assumption step and just add this little disclaimer, the proceed with caution. Okay. All right. Now remember, once you get to this part, stop. Okay, and put in your calculator these two things, right? You need one column with your observed values and one column with your expected values. Okay. Right. So remember, T stands for test statistic. Okay. What you're going to do is show one calculation, like one example of how the test statistic comes about. Okay. And then you're going to let the calculator do the rest of the work for you. Okay. So remember, the chi-squared test statistic is the sum of the observed values minus the expected values squared divided by the expected values. So here's my one example. I'm just going to use the very first demographic here. So my observed value was 32 minus my expected value, 40.32. I'm going to square that. Okay, say divided by my expected value, which is 40.32. And then you're going to say plus dot, 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 and then say equals. Okay, now once you get to this point, you need to run a chi-squared goodness of fit test in your calculator. Okay, so the way that you do that, after you enter your data in a list and you've named your columns, observed and expected, go back to just like a regular like calculator page, click your menu button, look for statistics, right? And then under statistics, you're looking for stat tests and you're looking for chi-squared GOF, okay? It will ask you to fill in like what's your observed list and what's your expected list, which is your the list that you already entered in your calculator. Okay, and then the other thing it's going to ask you for is degrees of freedom. Okay, so remember, degrees of freedom is the number of categories minus 1. So there's 5 categories in this problem, minus 1, so my degrees of freedom is 4. Okay, once you plug all that in, when you run the test, it's going to spit out a chi-squared value at you. So when I ran this test, the chi-squared value that my calculator gave me was 8.542 if I round, okay? Oh, and one other thing I forgot to do here is set my alpha value. So I'm going to set my alpha value at 0.05 because they did not give me a specific alpha value to use, okay? Remember, O stands for obtain p-value. You've already got that because your calculator spit it out at you when you ran your chi-squared test. So the way you write the probability notation is you do probability that chi-squared is greater than, it's always greater than, and then you put your chi-squared test statistic that you got right here, 8.542, and then just say equals, and then write the p-value that your calculator gave you. So my calculator gave me the p-value 0.074, okay, which obviously is greater than my alpha value, okay? So M stands for make a decision, right? My p-value is greater than my alpha value, so I'm going to fail to reject my null. And then last but not least, you have to state your conclusion in context. Okay, so I'm actually going to type this. So state your conclusion in context, right? So this is because the p-value is greater than alpha, we fail to reject the null hypothesis. Then you would say we don't have enough evidence to say that the stated distribution of students chosen is incorrect. Okay, so in layman's terms, what that means is, i.e., the principal, if you go back up to the actual question, you'd say the principal, there's not enough evidence to say that the principal is not choosing students according to demographics. So we can't say the principal isn't choosing students by demographic. Okay. All right, so that is your one other example for you of a chi-squared goodness of fit test. And I'll see you all in the next video. Bye, everybody.